Hey y'all, so I'm going to take some time to go over the key, I guess, for these glycolysis and redox reactions that we talked about in class. I'm also going to put this up in a PDF format for you, but this will provide some additional commentary that won't be present necessarily in the key. So the first step here, step one, glycolysis does not require energy. So that means that it's going to be a passive or facilitated diffusion across the membrane. And then once ATP gets added onto it, it gets converted into glucose 6-phosphate. This obviously is a reaction that involves a kinase, as we can tell with the presence of the ATP. And so a kinase enzyme is the one involved in that transfer. And typically, this question is always one that kind of hangs some people up, but the active site is the correct answer here. So active site is where substrates bind in order for a reaction to take place. Now, the addition, if we don't look at the ATP here, but just look at the conversion of glucose to glucose 6-phosphate, this is an endergonic reaction. In other words, the energy of this product is greater than the energy of the reactant. And those types of reactions require some additional energy input in order for the reaction to take place. Well, the release of the phosphate from ATP to form ADP, that release also results in the release of energy whose magnitude, or the amount of energy released, is greater than the amount of energy that's needed to add a phosphate onto glucose. And so this is known as energy coupling, in which an exergonic reaction, ATP to ADP, can be used to fuel an endergonic reaction. And that's what these responses down here indicate. In step two, we say that isomers have the same molecular formula, different structure, and glucose 6-phosphate and fructose 6-phosphate are isomers of one another. If you were to count up the phosphate, the hydrogens, the oxygens, and the carbons, you would find that they have the same number of all of those. In essence, what has happened is this oxygen breaks up, or between this oxygen and carbon, a bond is broken and then reformed between this carbon here and the oxygen, creating this, what looks like a largely symmetric molecule. On to step three. Phosphofructokinase catalyzes an exergonic reaction. Just like step one, that exergonic reaction can be catalyzed by the presence of ATP, which again, broken down to ADP, releases that phosphate and a whole bunch of energy. We talked in class about how PFK, or phosphofructokinase, is regulated both positively and negatively by different allosteric molecules. Molecules that bind to the active site and inhibit, or bind somewhere other than the active site, my apologies, and inhibit enzyme activity are known as allosteric inhibitors, which are also known as non-competitive inhibitors. If the molecule, like AMP, increases activity, these are known as allosteric activators. In step five, we have another isomerization. Again, the number of carbons, hydrogens, oxygens, and phosphate groups are the same between these two molecules, and therefore an isomerase catalyzes this reaction. In step six, we find a couple of different things here. We find that we're going to have the addition of 2 NAD, two of these molecules right here, and when these two interact with each other at the active site of an enzyme, we are going to find, one, the addition of phosphate. And notice here that this phosphate addition is not ATP, so these are inorganic phosphates, and so this is not a kinase activity. Kinases transfer phosphates, but we do get a reduction. NAD is the oxidizing agent, NADH is the reduced product, and so as NAD to NADH is reduced, this molecule here is oxidized into this molecule here. And therefore, since this is a redox reaction, the enzyme catalyzing this would be a dehydrogenase. Let me see if there's anything I've missed here. Yep, so glyceraldehyde 3-phosphate is oxidized to 1,3-bisphosphoglycerate. And in addition to electrons moving in these, redox reactions, hydrogen ions do as well. Okay. In step 7 and step 10, we find substrate level phosphorylations, which are catalyzed by kinases. Again, what we mean here is that we transfer a phosphate, or we find the transfer of a phosphate from reactant to ADP to form ATP here and also here, and those are our substrate level phosphorylations. Oh, I have a blank page here, so I'm just going to skip over that. My apologies. And then finally, to overview this process, this all takes place in the cytoplasm of a prokaryotic cell. We find that there are 2 steps in which there are substrate level phosphorylations because because everything occurs in duplicate after this step right here, as fructose 1,6-bisphosphate is being split into 2 different molecules. And then we get an isomerization of the glyceraldehyde 3-phosphate. Because everything is occurring in parallel, we say that there are 4 reactions total, yielding 4 ATP. In steps 1 and 3, energy is consumed in the form of ATP, and we get 1 step in which a redox reaction occurs, therefore leading to 2 reduced NADH molecules, or 2 reduced NADH coenzymes. Now, at the end of this process, we get 2 molecules of pyruvate, and a couple of things can happen to pyruvate. It can be reduced into lactate, ethanol, or some other fermentative byproduct in which NADH is regenerated into NAD. We'll talk about that later on. Or pyruvate can enter into the Krebs cycle, also known as the tricarboxylic acid cycle or citric acid cycle, in which it can be further oxidized in order to produce more NADH and more FADH2, or more reduced coenzymes. And those coenzymes then can provide electrons and hydrogen ions to the electron transport chain ultimately. Now finally, I wanted to just take a few minutes to cover these oxidized and reduced reactions. I started with these coenzymes here just to remind you that NAD plus is the oxidized form, whereas NADH, this hydrogen here, indicates not only that hydrogen has moved, but electrons have moved. Therefore, this is the reduced form. Gain of electrons equals reduction. Same here, FAD is the oxidized form, and then the addition of 2 hydrogens, also with electrons, would be a reduction. When we look at these reactions then with additional molecules, here's an example of C4H6O5 plus NAD going to C4H4O5 and NADH. NADH is the reduced product, therefore that would make this one the oxidized product. And we always say that an oxidized reagent or oxidized agent will be ultimately reduced. And so NAD is the oxidized form, NADH is the reduced form. I also want to point out here that in this carbohydrate, we lose 2 hydrogens, which again is indicative of electrons moving as well. And so this molecule is losing electrons, therefore defining this one as the oxidized product. And because this has donated the electrons, this reagent here, or reactant, is the reducing agent. In this bottom one, FADH2 is the reducing agent, as it's giving electrons and hydrogen ions to ubiquinone to form ubiquinol, and therefore FAD is the oxidized product. Ubiquinone is the oxidizing agent, and ubiquinol, having gained electrons, will be the reduced product. If you have any questions, please come check with me or review this key on your own. Have a great rest of the day.